Have you ever picked up a rock, maybe a piece of granite, and just stared at it? All those different little crystals, the pinks, the whites, the blacks, and then thought, wait a minute, this all came from one single, uniform batch of molten magma? How is that even possible? How does a simple liquid create something so complex? Well, today we're going to crack that puzzle. Okay, take a look at this rock right here. It's a perfect example. You see those sharp, almost snowflake-like white crystals? And they're just floating in that dark, glassy-looking background. The wild part is, both of those things, the white crystals and the dark matrix, they came from the exact same liquid melt. So how on earth does one liquid split itself into two completely different solids just by cooling down? And that really is the fundamental question, isn't it? If you were to melt this rock back down, you'd get a single, boring, uniform liquid. But when it cools, boom, you get this beautiful complexity. To figure out why, we have to look at some really basic laws of the universe, the rules that govern how pretty much everything cools down and changes. Right, so the answer isn't some secret geological trick. It's actually rooted in the fundamental principles of thermodynamics, basically, the laws of cooling. And these laws apply to everything, from a star forming in space to your coffee getting cold on the counter, and yep, to a chamber of magma deep inside the Earth. It all boils down to this one simple but super powerful idea. You could almost say nature is, well, it's kind of lazy. Every single thing in the universe, whether it's a huge boulder on a hill or a blob of hot magma, it just wants to settle into its most stable, lowest energy state. For that boulder, it means rolling down to the bottom of the hill. For magma, it means getting rid of all that intense heat energy. And scientists have a name for this ultimate chill zone: stable equilibrium. For a hot, chaotic, messy liquid like magma, the most stable thing it can possibly become is a cool, ordered, solid crystal. So forming crystals is just the magma's way of finally getting to relax and reach its stable equilibrium. And listen, this isn't just some neat theory, it's the bedrock of petrology. As this quote from a major textbook says, this constant push toward the lowest energy state is what drives the whole process of how igneous rocks are born. So the big takeaway is, the magma wants to become crystals. It's its destiny, in a way. Okay, but that still doesn't explain why we get different kinds of crystals from the same liquid. To get to that, geologists realized they needed a tool, a way to predict what's going to happen as that magma starts losing its energy. They basically needed a map for the journey from liquid to solid. And I'm not talking about a map with mountains and rivers. I'm talking about a map of the states of matter, a chart that shows you, hey, under these conditions, you're a liquid, or under these, you're a solid. This incredibly powerful tool is called a phase diagram. And here it is, the master map. This is a full-on 3D phase diagram. It plots the three really big variables: temperature, pressure, and the chemical composition of the magma. Every single point on this crazy-looking surface tells you exactly what state the material is in. But, yeah, this is a little much for our purposes. Let's simplify things a bit. To really wrap our heads around this, we can kind of squish that 3D map down into a 2D version. And the way we do that is by looking at a much simpler kind of magma. So we're going to look at what's called a binary system. All that means is it's a magma made of just two main minerals. By doing this, we can just set pressure aside for a minute and really focus on that dance between temperature and composition. All right, now this diagram tells us everything we need. It's pretty simple. On the side, that vertical axis, you've got temperature, getting cooler as you go down. Along the bottom, the horizontal axis, that's composition, going from 100% of one mineral on the left to 100% of another on the right. Now that big V-shaped line, that's the star of the show. It's called the liquidus. Anywhere above that line, everything is 100% molten. The second a cooling magma touches that line, crystals start to form. And it's by tracing the path of a cooling magma on this very map that we finally find the answer to our puzzle. We find this one very special place, a kind of chemical sweet spot where all the magic happens. So let's follow the journey. Picture a drop of magma way up high in that all-liquid zone. It starts to cool, so it moves straight down. Then, bam, it hits the liquidus line on the left side. The first crystals, let's say they're mineral A, start to form. Now here is the absolute key. Because we're pulling mineral A out of the liquid, The liquid that's left over now has more mineral B in it. This changes its chemistry, which forces it to slide down that V-shaped curve to the right. As it keeps cooling and making more mineral A crystals, it just keeps sliding down that slope until it hits the very bottom point of the V. And at that one specific spot, something incredible happens. Both mineral A and mineral B start crystallizing out at the exact same time.
This special spot, this chemical sweet spot, it has a name. It's called the eutectic point. It's the lowest possible temperature that this mixture can stay liquid at, and it is the one and only combination of temperature and composition where two different minerals can pop out of a single liquid together at the same time. This is it. This is the answer to our puzzle.
So we've got the theory. We have this cool map that predicts exactly how this should all go down. But does it actually happen out there in the real world? Let's connect our diagram directly to an actual rock and see the proof for ourselves. And here is that connection. It's awesome. On the left, there's our diagram, our prediction. And on the right, that's a microscopic view of a real rock. Just look at that intricate, interwoven texture of the two different minerals. That right there is the telltale signature of eutectic crystallization. It's the physical evidence of two minerals growing shoulder to shoulder at the same time, exactly like our map said they would. And this isn't just some rare, weird thing that happens sometimes. The eutectic process is absolutely fundamental. It's exactly how we get the classic salt and pepper look of granite, or those complex textures you see in diabase. It is the main tool nature uses to turn a simple, uniform liquid into a complex, beautiful, multi-mineral rock. So think about it. We started with a simple question about a cool-looking rock, and we ended up at a universal law of chemistry and physics. Once you learn how to read these phase diagrams, you can start to decode the secret history of how a rock was born. It really makes you wonder, what other amazing stories are written in the stones all around us, just waiting for us to figure out their language?